Not happy. Come on. Not happy. There we go. Okay, so let's try it again. What this look like? Like this. Something like that. Not bad. Okay, so this was this thing. So can you find, using geometry, can you find that volume? So what is that volume? Just using pure geometry, like before you knew any calculus. What is that volume? Go. So work that out, and I'll rewrite the integral we came up with last time. Oh yeah, so the volume of a sphere is what? Remember? 4/3 pi r cubed. Should have gave you that. So if the volume of a sphere is 4/3 pi r cubed, what would the volume of this thing be? Yeah.
So it's the volume of a sphere of radius 3 minus the volume of a sphere of radius square root 6
Okay.
divided by 4.
He wants the volume of a sphere of radius 3 minus the volume of the sphere of radius radical 6, and then 1/4 of that. Agree?
Yeah.
Anyone get it? 1/4 of 4/3 pi times what? 27? Oh, that again. Minus 4/3 pi times radical 6 cubed. And anyone got that? So the force can go away. So we get what? That 9 pi minus whatever that is. Radical 6 cubed over 3 pi. What is that? That's 6 radical 6, right? So 2√6. Or pi times 9 minus 2 radical 6 would be the volume of this band shell kind of thing. Okay, so then recall that we set up the triple integral to do that, and we said if we want using a triple integral to find volume, we're going to make our function 1, right? And then it would be dv, right? dv was, we derived last time, rho squared sine phi, d rho, d phi, d theta. And so phi goes from, rho goes from radical 6 to 3. So out from the origin, and then phi goes from 0 to pi over 2. And then theta goes from negative y-axis around to, or negative x-axis around to positive x-axis would be pi to 2 pi. So do you recall that? Does that make sense? Okay, so if we do the math on this, we should get this, right? So testing our triple integral to find volume versus our just plain geometry to find volume, right? So here we go. Integral with respect to, antiderivative with respect to rho would be rho cubed over 3 sine phi, and that would be from square root of 6 to 3. And what would that be? That'd be our 9 sine phi minus 2 radical 6 sine phi. Check my math. Is that right? And then now we have d phi, d theta, double integral. So remember in rectangular coordinates, we thought about these triple integrals as surface to surface for the inside integral, and then an outside double integral for the projection into the plane, right? Spherical coordinates and cylindrical coordinates, we don't think about it. We just think of it as, just get your 3 sets of limits in order. So we look at what rho varies from, then what phi varies from, and theta varies from. So with these cylindrical and spherical coordinates, we don't take that same approach that we did with rectangular, where we did the outside double integral. We don't really do that. Okay? So with respect to phi, antiderivative with respect to phi would be negative cosine. So it would be negative 9 cosine phi. Or we could do just 9 minus 2 radical 6 times negative cosine phi. Is that right? And that from 0 to pi over 2, which would be what? Negative 1 minus 1. So negative cosine of phi would be positive 1. And negative cosine of 0 would be negative 1, so what would we get there? We're going to get negative 1 minus negative 1. Yeah.
Is it 0 or is it supposed to be pi?
Yeah, sorry.
The cosine of pi over 2 should be 0, right?
Yes, right. So this is 0 here. But I'm thinking pi, right? So this is 0 minus negative 1, is that right? This is 0. Thank you. Which just gives us positive 1, just this thing. And that from pi to 2 pi. D theta. And then so that's just going to be 9 minus 2 radical 6 times theta. From pi to 2 pi. And that does it, right? That gives us that. Equals. Okay, so showing that our triple integral was correct by comparing it with just plain geometry. Any questions on that? So I left this off, so this still is pi to 2 pi d theta equals. Anybody? Question? Okay, harder example. Let's do this next one. We want to set up the integral in spherical coordinates. Maybe this time we're integrating some function f. Yeah, we are. Right, so I'm integrating this function. This is our f function, but as x, y, and z. Enough of that. Try again here. Okay, so this is our f, x, y, z. And here we're going to integrate that function, x squared plus y squared z squared, over, for all points in the solid, inside x squared plus y squared equals 4, below z equals 5, and outside x squared plus y squared plus z squared equals 4. So you need to make sure you can draw that, right? We worked hard on our surfaces for problems like these and in the future. So make sure you can draw that solid. And then for all those points, E, we're going to integrate that F. X squared plus y squared plus z squared. But the real challenge here is setting up the limits of integration. So make a good, large, precise drawing, and then start working on what you think. So we're going to set up this triple integral in spherical coordinates. Okay, so let me give you a tip here. So we still want to use the archer. And so if the archer is firing and rho is the first variable, then where is the archer standing? Or where's the archer firing from? Right, so the archer is going to be at the origin, firing out away from the origin. And we're still going to think like surface to surface. So at what surface does the arrow pierce into the solid, and then where does the arrow leave the solid? So we still want to think surface to surface, but now it's firing from the origin out. Okay, so where does the arrow pierce into the solid when the archer fires from the origin? Where does the arrow pierce into this solid? The sphere? Always? Does it always enter into the solid through the sphere? Yes. Okay. And so that would be rho equals what? 2. So that sphere, x squared plus y squared plus z squared equals 4, is the same as, well, that's rho squared. Rho squared equals 4, and that's sphere of radius 2. And then where does the arrow leave the solid? So where does the arrow leave the solid? What surface? Z equals 5?
Sometimes leaving out of the light side.
Okay, so for low values of phi, do you see that the arrow leaves through what? Z equals 5, when phi values are low, near the z-axis. But for greater values of phi, what happens? It goes out the cylinder. Do you see that? So therefore, we have to split because of the upper limit of integration for rho. Where the arrow leaves the solid is split between z equals 5 and the cylinder. Do you see that?
We're shooting from the origin and down.
And what is x squared plus y squared plus z squared in terms of spherical coordinates? Rho squared. So we'll just write that now. So it's going to be rho squared times another rho squared sine phi d rho d phi d theta plus, and we're going to have another one. And then that's going to be the same. Okay, so we said in terms of rho, the arrow firing the arrow from the origin, it always enters the solid through the sphere, right? So it's going to be 2 here and 2 here. But then, depending on the angle phi, depending on the range of angles phi, we're going to have a different exit point. Sometimes for low values of phi, it's going to be z equals 2. And for higher values of phi, it's going to be the cylinder. So what's the breaking point in terms of phi values? So z equals 2. And then how can we express the cylinder? X squared plus y squared equals 4. He wants r equals 2. Is that right? Yeah, because that's x squared plus y squared is r squared, right? Oh, z equals 5, so not 2. Right? Cylindrical coordinates is based on r. Constant values of r gives you the cylinder, right? All points 2 away from the z-axis is that cylinder. X squared plus y squared equals 4. Okay, so what is the good. There's going to be some, so for low, like I said, low values of phi, we're exiting out z equals 5. Well, what is that in spherical coordinates? Well, we need to change that into spherical coordinates. What is z in spherical coordinates? Rho cosine phi equals 5. So therefore, rho equals 5 over cosine phi. Or, what's 1 over cosine? Secant, right? Secant. So you could do 5 over cosine. That's perfectly fine. Or 5 secant. Right? So the distance that you go through that plane depends on phi, right? You're going to, as phi increases, you have to go a farther distance. You see that? So that's why that rho value depends on phi. So I'm going to have from 2 to 5 secant phi. And that's going to be for phi values from what to what? When phi goes from 0 straight up to what? So the question is, where do we stop exiting out the plane and start exiting out the cylinder? So we got to figure that out. So it's going to be at this phi angle right here. Right? At this phi angle. So we've got a triangle, right? We've got a right triangle. The height of that triangle is 5. So I'll just draw it again here. The height of the triangle is 5. This leg of the triangle is 2. And that's my phi. So phi equals what? Arctangent of 2/5. So that's, we want to exit out z equals 2, or the 5 secant phi, when phi goes from 0 to the angle arctangent of 2/5. Does that make sense? For that range of angles, for phi 0 to 2/5, we exit out z equals 5, and that z equals 5 is the same as rho equals 5 secant phi. Phi. Secant phi. Okay? And then theta from what to what? That's easy. All the way around, 0 to 2 pi. Okay, then the other one, we're going to go from 2 to what? So r equals 2. What is r equals 2 in spherical coordinates? Rho sine phi. Therefore, rho is 2 cosecant. 2 over sine phi, or 2 cosecant. So we're going to go, rho is going to go from 2 to 2 cosecant phi. For what angles phi does that happen?
So we're going to start now at arctangent of 2/5. He suggested that we're going to go from arctangent 2/5 to, it's going to be to pi over 2. Right? Because the last one is going to be like this direction, entering the sphere, exiting out the cylinder on the xy plane, basically. And that's also from 0 to 2 pi.
Okay, so did I lose you anywhere? Please ask. Does it make sense? So the reason that it has to be split up into 2 is because of rho, and that's the where the arrow would leave the solid coming out from the origin. So it enters in the sphere everywhere, but then according to the angle phi, it's either going to exit out the top z equals 5, or it's going to exit out the side cylinder r equals 2. So that's why we had to split it up, according to those range of angles for phi. Yeah, Jorge. Good.
When I approach this problem using like cylindrical coordinates.
Yeah, how about using cylindrical coordinates?
Prefer or not?
About the same.
About the same.
Easier.
Easier.
Would it be 1 or 2 in triple integrals?
It'd be 2, but 2 really easy
Was
ones.
it 2?
1 for cylinder and 1 for
So
sphere.
dz
It goes from 5 to
r dr d theta. So what about z?
that's
From bottom surface to top surface.
1 or 2 integrals?
just 0 to 5.
Not
Not
0.
Well, you could do like the integral of the cylinder minus the integral of the sphere.
No, you don't. No.
It would just be square root of
Mhm.
4
You
minus.
don't do it at a minus. So dz means bottom to top, right? Bottom surface to top surface. What's the bottom surface? Just the sphere. What's the top surface? Z equals 5. And then we do what? Okay, so I think I said earlier in cylindrical coordinates you don't project. You do project, right?
Cylindrical coordinates. Now we're going to project into the xy plane and do the r theta projection. 1 or 2 integrals?
1, right? So this is definitely easier in cylindrical coordinates. Go from the sphere, z, to z equals 5. And then dr d theta is just going to, this is just going to project as what? Solid disk. So r goes from 0 to 2, theta 0 to 2 pi. So definitely easier in cylindrical coordinates. Why? Because it's a cylinder, right? It's basically a cylinder. The only kind of hard thing about it is the bottom, which is a sphere, but you just solve it for z, right? You just solve that for z, and you get square root of 4 minus r squared. And that's not really that hard at all. Yeah.
So, like, if we have this question on test, it would indicate if we need spherical or cylinder.
Maybe. I mean, no, you should be able to do it both ways and then also know which way is easier. Yeah.
Okay.
Yeah. Or I might specify, do it this way. Yeah. So it might specify, do it this way or do it this way, or it might say, do it the easiest way. Other questions? Okay, let's, so that's spherical coordinates. That's a good example there, that last one.
And then, so then what you did in recitation yesterday, you did a couple spherical problems. So then, and the actual written homework, you'll do them both in spherical or both in cylindrical and spherical. And so then it'll be, you'll see how it works out. But make sure you're really knowing whether or not these get split up or not. That's the key. Sometimes an integral in spherical coordinates would be easy in one integral, but in cylindrical, you'd have to split it up. And then vice versa, like this one. Much easier in cylindrical, one triple integral. Do it in spherical, you got to split it up. So make sure you're analyzing that carefully before you just start writing things down. Any questions? And again, reminder, we have our test a week from today. I'm going to post the review materials. So you can get started on that. Next Thursday's recitation will just be study session, okay, for the test. But study before that, please. Don't wait till Thursday. That's my biggest piece of advice for doing well in the exam is start studying early. Study many times, and then you can work on getting your questions answered a couple days before the test. All right, we got next topic here. Can I erase? Last chance, questions. Okay, so a big theme in this course is all different kinds of functions. Okay, that's a big theme in this course is all different kinds of functions, specifically single variable versus multivariable, and real valued versus vector valued functions. And those different options create lots of different types of functions. So for each of the types below here, identify the conventional algebraic form. For instance, in this course, we've seen something like z is a function of x and y. That's what I mean by conventional algebraic form of a particular function. How it graphs, and in what coordinate system. So I want you to go through each of these, identify its common algebraic form, what it typically graphs as, and in what coordinate system it has that graph. So go, just take a minute to do this, see, and definitely discuss if you need to. Let's just talk through them. So for time's sake, what is a single variable real valued function? Y is f of x, right? And what coordinate system does that graph in? R2, and it graphs as a curve. Curve in R2. A multivariable real valued function. Commonly, we write that how? Algebraically. So multivariable is referring to the independent or dependent? Independent. Real valued? Dependent. So one value from a combination of multiple independent variables. So in our course, we've seen the commonly z equals fxy. And how does that graph, and where does it graph? What do you think? Surface and R3. It's been most of the course for us, all right? A single variable vector valued function. Okay? How do we write that symbolically? Remember how we wrote those symbolically? Right. And that's vector. RT. So we could have that in R2, or we saw those also in R3. So how does this, what typically was the graph in R2 of a single variable vector valued function? Remember what this was in R2? If we put all the vectors that were the outputs in standard position and then let t change, it sweeps out a curve, right? Like a laser light show. So you get curves here, either a curve in R2 or a curve in R3. Finally, a multivariable vector valued function. What would that be like? So instead of r of t, it would be, go ahead. I think so. It's going to be a vector valued function like this, but instead of r of t, it's going to be like we have two variables here, and then each of your components of your vectors will be functions of both will be multivariable functions. Does that make sense? So here's with two independent variables. Then each of your components will be multivariable real valued functions. And those will form the components of the resulting vector. Or in R3,
You'll have three. You could have three input variables, and then each of your components is a multivariable, three multivariable function that form the vector. So the question is,
what are the graphs of these? So these are the ones we haven't seen yet.
all of this we've seen so far in the course. First three we've seen. Multivariable vector valued functions,
We have not seen yet. So here's just a little preview. So here's the point 0, -2. X equals 0, y equals -2. That's my independent. And for that, I get a vector. And then if I change my location, so here's x equals 1, and say y equals +2, I get a vector. Here's x equals -1, y equals 0. So my independent thing is now multivariable, which represent locations in the plane. And then for every location in the plane, I get a vector. So what is that?
A vector field. That's what these are, vector fields. For every location or ordered pair x and y, there's a specified vector. So this is, if I showed every vector in this vector field, all you would see is just blue. So I'm just showing you, this is just showing you like some of them to get a feel for what the vector field is. You can't show all of them because then all you'd see is just a blue block. There'd be vectors everywhere.